slower rotor bars. Consider a theoretical scenario where the physical rotor successfully accelerates to match the stator's magnetic field at exactly 1500 RPM. If the field and rotor spin at the same velocity, the relative motion between them vanishes. Without that relative motion, the magnetic flux lines instantly stop cutting across the rotor bars. The induced current vanishes, the magnetic field collapses, the attractive force fails, and torque drops to zero. Reaching synchronous speed is physically impossible under load. If the motor ever caught up to the field, it would instantly lose power and decelerate. This mandatory physical lag between the speed of the magnetic field and the mechanical speed of the rotor is known as slip. Engineers calculate this lag as a percentage, comparing the synchronous speed to the actual rotor speed. At a standstill, slip is at 100%. This maximum relative motion induces massive current spikes to overcome the motor's static inertia. Slip is a dynamic, self-regulating mechanism. As a mechanical load slows the rotor down, the slip percentage increases. This chart illustrates that relationship. As the motor load increases, the current loading percentage rises linearly, providing the torque necessary to move the heavier load. Slip acts as the dynamic engine of power transfer, physically regulating exactly how much current the motor pulls from the grid to sustain its rotation. This torque speed curve maps a motor's physical limits. Starting at locked rotor torque, the brute force when first energized, it rises to breakdown torque, the maximum force before stalling. Normal operation is this steep drop-off, achieving full load torque with minimal slip. Operating outside of this narrow window will lead to either a mechanical stall or a rapid failure of the motor's thermal insulation. Because induction torque is driven by load-dependent slip, its exact RPM is inherently unstable and fluctuates whenever the load changes. For precision tasks like CNC machining and robotics, speed must remain perfectly constant, regardless of the resistance on the tool. This requirement for absolute stability is met by the synchronous servo motor. Instead of inducing current in a cage, synchronous rotors use permanent magnets to physically lock into step with the stator's revolving field. Because these fields are locked, the motor achieves zero slip, turning at the exact speed dictated by the frequency of the grid. Induction motors dominate the world through rugged, slipping force, but achieving the absolute peak of digital control requires abandoning slip entirely for the rigid lock of synchronicity.
Namaste. Thanks for watching. Stay tuned for more.